Hey everyone, so today's video is going out earlier than expected. I figured out my bug in the get try diagonal code, and just because it was rough for me, I am going to honestly just do all the code again from yesterday. Um just for funsies, just to have it get it cemented into my brain as well. Alrighty, let's do this. Okay, so code, let's start with our functions. We'll do inner product, a comma b, on turn, a, I, comma, oh, a, b, I in range when a, actually, um, uh, that is the inner product. What is the outer product? A, comma, b, colon, return a nested list, a underscore n times b underscore n, uh, b underscore n in b, b underscore n in a. Is that correct? Yeah, so each row in A multiplied by each element in B to give the first row in the matrix, in the outer product matrix. The second, you know what, let's just test it. uh, outer product 1, 2, 3, 4, 5, 6. 4, 5, 6. Oh, one, ta. Yep. Yep. Inner product, outer product. Working fine. Let's do L2 norm of the vector. That's pretty easy. We do a sum. We do the square root. And the sum is the square of each element in B. Hallelujah. Normalize that being, that's pretty easy. Well, we need scale as well for that. So that scale back up m comma b, return m times n or n in b. Um, scale, oops, return scale 1 over L2 norm of b, comma b. We need to scale matrices as well. So m comma big M to denote the matrix. We return a nested list. M times n for n in row. For row in M. Pretty straightforward. We need to be able to sum vectors. So we're going to do that. A comma b. Return AI plus BI for I in range 1. Okay, yep. No, I wasn't doing this yesterday. I'm not doing it today either. I'm not doing any like making the code robust or anything like that, wherein, it checks of things being compatible in shape and stuff like that. Right now, I'm starting to enter a realm where it's like somewhat of a challenge for me. Mostly in understanding. I think now that I understand how solar reflectors, it wasn't actually too bad to do the code. But if you're following along at home, feel free to do that, give yourself an extra challenge. Um, you need to be able to get the identity matrix, so let's do that. It's a nested list again. 0 if I not equals j, else 1 for j in range len shape. Let's go for I in range len shape. Let's test that one because I'm a little less confident it's correct. Oh, that's why. Yep. All right. Identity matrix is getting that. Uh, let's do that sub. I a return nested list. I j minus a I j for j in range len I 0 for I in range len I. Let's do that. We're going to test that one out as well. So I think that should be fairly easy. 1, 2, 3, 4. 0, -2, -3, -3. Yep, that's correct. MathSub is working fine. Let's go back to this. Just gonna scroll down to the example. Yeah, I need to be able to embed the matrix as well. But let's go ahead and build the reflector. Make sure we're building the reflector right, and then we'll do the embed matrix. So build reflector. A. Oh, sorry, not A. This takes a vector. Shape equals len b. um, alpha equals v0 divided by absolute value of v0, which just leaves me 1 and the sign times L2 norm of v. Actually, I'm gonna switch this to x. Shape alpha. Um, oh, we need to get the basis vector as well. Get basis back. That also just takes shape. Return 0 if I not equals 0, else 1. For I in range len shape. Alrighty. So we'll move on to the next one, guys. Okay, alpha. Okay. I have X ready to go. So X. You know what? Let's start with the innermost thing. We're just scaling alpha with the basis vector of shape. Scale back. I'm gonna wrap that entire thing. X plus alpha E1, right? Yep, X plus alpha E1. Back sum. That equals U. And V is equal to. I could skip B. So I can just throw this into normalize back. Just a bunch of nested function calls here. Nah, because then I just have to write it out and compute it twice. Order product V comma V. Scale math 2 times this. Uh, Maths up, get identity, scale matrix 2 times the order product. Oh, we can just return that. That's building a reflector. Let's check with the vector. 1, 2, 2. Oh, I did the range lens shape thing again. Yep, this is correct. Def get HH by diagonal. Alrighty. So now for the main event. Hmm. Oh, we need to embed. We need to write some code to embed a matrix first. I H. How do we embed this? This one is a bit of a toughie. I've done it. I've made this mistake a couple of times. Plus one. Wait, no, I think. Can I just this? Okay. I have to return it, even though it is changed in place. Sake of completion, making code in shorter steps easier. Embed matrix. Sorry if I got a little too quiet, guys. My dad was in here doing some stuff, so I was trying to be quiet and not disturb him. So, in the meantime, let's get identity. Let's say 3, and let's embed 1, 2, 3, 4. There you go. And no, this is not correct. Um, should be +1, right? Pretty sure that's the case. Yep. Let's do it with the bigger matrix, and why was this working with a 3 and not with a 5? Is negative shape +1 or -1? -1 doesn't make sense, does it? No, it doesn't. Hmm. Always goof this up. This is the hard one. How are we embedding this matrix? I am missing something here that I am not understanding. So negative I is -5. Oh. Hmm. I negative I matches up, but H negative I does not match up, right? No, it does. No, we're going len, not I, len H, right? That makes sense. And then we do the shape +1. Yeah, that makes sense. Okay, maybe not. Actually, no, negative shape makes sense. Why am I missing the value? Ah, yeah, because it starts at 1 and ends right there, so I need to actually add 1 here to the iteration. +1. There you go. I don't know why I always fuck that up. It makes perfect sense once I do it, but I always screw it up. Anyways. Def. Okay. I think now we have all the pieces in play to get that tri-diagonal build. What's up? Hmm. H equals len A. Sim equals A. For I in range shape. Actually, I can just do the walrus operator here. Len A. We get the reflector, and that's embedded right away. No, let's get the vector first. To build the reflector, we need to actually get the column I comma some matrix return row I for row in A. Okay, so we have to get the column. Yep. What's up? Yeah, I'll come. All right. Okay. Cool. Is Minecraft coming? Okay. Get call I comma A. I so 0 it'll be the first column, second column. That's what we got to do. I A I plus 1 through. That's the vector we need to build the reflector out of. The vector reflector. We build the reflector from this, right? And we embed this in the identity matrix shape. And that is HBLK. Oh, no, that's not HBLK, that's just H. HBLK is just the reflector block. You know what? I am block. There you go. I just made that change because like part of it when I'm doing the code, like obviously it just makes it easier to code it when you just break out every piece into a small thing and then like do this, do this, do this, do this, right? It may not be the most efficient in all situations, like we saw with matrix multiplications and the three nested loop algorithm. Oh, which reminds me, I need to do matrix multiplications. Ooh, shoot. So sim equals 2 matmuls basically. Uh, Alright, I need to use the washroom, boys. There's gonna be some dead silence here for a moment, because, uh, actually, let me see if I can pause the recording. Oh, I totally can. And I'm back. Boys, what's up? Alright, let's go. So, I need to do matrix multiplication. Now, I could do it the way I originally did it, but I'm gonna challenge myself and try and remember. Well, it's not that much of a challenge because I did it yesterday by myself, even though I didn't show it in the video. And it's mostly going to be us multiplying H and A. So I'm just going to keep those same symbols. All HA. Right, we'll go for the classic three-nested loop algorithm, for which we need to pre-prepare the list, which is I'm just going to call the matrix M. 0 for underscore and range len 0? No. H 0, right? The number of columns in the first and the number of rows in the second. For underscore in len A, right? So the number of columns in the first needs to match the number of rows. Because wait a second. No. Because it's the matrix of m by n is multiplied by a matrix of n by p. Your output matrix will have shape m by p, which means that it is the number of rows from A, number of columns from B. So this is actually flipped around, H and A. So it's A, H. I'm just presuming it's going to be of compatible shape. I'm not doing the testing and stuff here. So for M in range when M is the number of rows in H, for N in range len the number of columns in the first or the number of rows in the second. We'll just go for the number of rows in the second. For P in range len number of columns in the second. Once again, I'm not doing any testing or anything like that. M P plus equals H M N times A N P. Yeah, I'm pretty sure this works. Let's just test it to be safe. Oh, I don't return it. That would be a problem. Yeah. So let's see if that's correct. 1, 2 times 1, 3. What the flip? 7, 10, 15, 22. Row column. So row column would be 1, 2, 3, 4, 1, 2, 3, 4. So first row, first column would be 1, 2, 1, 3. Oh yeah. 1 times 1 is 1, and then 2 times 3 is 6. So that 6 plus first row, first column is the first element. So 6 plus 1 is 7. So that's 7. Okay. Then it's the second column. So it's 1, 2 times 3, 4. So 1 times 3 is 3. 4 times 2 is 8. 8. Okay. How's 8 plus 3, 10? 1 times 2 times, sorry, 2 times 4. So it'll be, yeah, okay. 1, 2, 2, 4. So that's 1 times 2 is 2, and 2 times 4 is 8. 8 plus 2 is 10. Yeah, okay, this works out. Yep, okay. So the matrix multiplication is fine. And then the similarity is essentially two map moles within each other. The final piece being H, and then I'll be HA. Oh, I should use sim instead of a, and do that here as well. I believe that's it, right? Oh yeah, we have to make sure that this actually cuts out. I think it's -2. Um, H2A2, H2, yeah. All right, let's test it out. All right, let's just punch this bad boy in. 4, 1, 2, 2. 1, 2, 0, 1. 2, 0, 3, 3. 2, 1, 3, 4. And looks like we got it right. Let's let's do a rounding function as well. Def round mat m colon return n round n3, because remember, like even here, everything like that is 0 is actually just numbers that are less than 10 e neg 6, -16, sorry, not 6. Which essentially means that it's just a really small number. And if you did the math with like real numbers, like using fractions and maintain that fractional representation, it would have like a very, it would essentially equate to 0 in the places where you can express them as a rational number. Um, rational numbers being ones that can be, anyways, whatever. Um, because of floating point precision, computations that, if done by hand and represented appropriately in the appropriate form, would actually equal to zero, because of floating point precision will not be exactly zero, but we get really, really close to zero, which is essentially equivalent. And that's what we're gonna do. That's why we're just rounding it here to 3 digits, so that all the 10e neg 16s, let's even round it to 4 digits, or even 5 digits. Let's do five, just because we're having a little bit of fun. For n in row, for row in m. I'm just gonna do that. Gonna encapsulate this whole thing in round mat. Okay, 4 negative 3 0 0, 4 negative 3 0 0, negative 3 6.44, 1.11665, 0, 0, 0, 1.1165, 0.94169, 0.861386, or 19, whatever, 0, 0, 0.86139, 1.61386. Alrighty. Are the signs correct? Because the bug that I realized in the middle of the video yesterday, or well, towards the end of the video, was just me looking at it was with the tridiagonal, essentially led to the signs being wrong. So I want to just double back: positive, 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 negative, negative, positive. All right, so that's this video. That's our remix. It's basically almost exactly the same as the video from yesterday. I just kind of wanted to do it again. It'd be more fun, just kind of have like cement into my mind. Um, I'll be honest, I this is the code that I will turn into lesson 11 essentially. So this is kind of the end of like this behind the scenes for getting to lesson 11, but I'm going to continue this for a little while, and I'll just rename it On the Road to Lesson 12, and start learning QR factorization, because I want to put a little space between myself, like right now, and when I do it next, just so that I really cement it if I come back to this after a few days, rather than just coming back to it right away again, like later tonight or tomorrow or whatever. So thanks for joining the remix. Have a great one, everyone.